thank you for your kind introduction, and I would like to thank the organizers for the very kind invitation to this very interesting meeting. Today I would like to talk about a joint project with Yoshi Giga, who was the first speaker, and Michał Łasica, who is in the audience. And we would like to derive the boundary conditions as a limit of gradient flows. We studied a very specific gradient flow in our paper, which is the gradient flow of the total variation with dynamic boundary conditions, and we studied properties of solutions. However, we weren't quite satisfied with the derivation of the dynamic boundary conditions, and I would like to pick up this topic today. But I would like to start with a simple setting of the heat equation. And my point is to derive it as a concentration phenomenon. We will be interested in the strong setting as well as the weak one. And we will use slightly different approaches, but the main idea is the same. We would like to see some concentration phenomena. Suppose we are given a functional E, okay, on a Hilbert space H. And what we will vary is the metric we will consider on this space. As a matter of fact, this is a weighted space, a weighted metric, and the definition is clear. And what is the point is that at the boundary we will see a weight whose width is epsilon, and the weight is a power of the reciprocal, and we will play with this power to see different things. And let me stress one important thing. We will consider very simple domains, which is a flat cylinder. Flat meaning we take a flat torus and take a cross product with an interval. This is just for the sake of simplicity, but you might ask what happens in the more general domains, and we don't know at the moment. Excuse me. What happens? Yes. Here. And as I said, I would like to talk about weak and strong solutions. And when we are talking about weak form of the gradient flow, let me specify the gradient. It is just the Dirichlet function. And if we keep in mind the form of the metric, we obtain the following set of equations. And since we haven't specified any boundary conditions in the gradient, we will pick up so-called natural boundary conditions. And of course, we are interested in the weak form, so we perform just the standard thing multiplied by, we multiplied the equation by test function and performed integration by parts. So just for the record, let me write these equations. Okay, and when we are talking about the strong version of the gradient flow, we change slightly the setting because we are introducing a weight into the Dirichlet function. And this weight makes the problem slightly degenerate. Because if we compute the gradient flow of this energy, we will pick up the following equation. But let me stress what I mean by a gradient flow. I mean the gradient flow in the sense of the convex analysis. I have to compute the subdifferential of our energy. And let me stress that the subdifferential is computed with respect to a very specific topology. And let me stress one important thing related to equation 5. I didn't write here any boundary conditions, and this is not a mistake. Here, the boundary conditions are implicit. This situation is similar to considering a parabolic problem or elliptic problem on a whole Rn. You do not usually specify the boundary conditions at infinity. You specify them in an implicit way. In other words, we will see also competition between degeneracy of the problem, induced by the weight, and singularity induced by the weight. Okay. So I will start with simple solutions, simple questions. So I will study weak problems. So let me make my weight specific, which means here that the height of the weight is the reciprocal of the width. And suppose we have a sequence of weak solutions to the gradient flow of E, again with our choice of the metric, then we have enough a priori estimates to claim that this sequence converges weakly in the natural topology, and U, the limit, is a unique solution to the gradient flow. I mean here, the gradient flow of, the heat equation with the dynamic boundary conditions. So the main point is to prove the last part, because existence of solutions comes from more or less immediately from the parabolic version of the Lax-Milgram lemma. And the a priori estimates are, as a matter of fact, quite easy. We multiply our equation by a test function, which is a solution, to get the estimate. Okay, and this estimate is sufficient to select weakly convergence subsequence. Fine, this is fine. However, we have to worry about what happens at the boundary. If we look at this identity, we see that the places where the weight plays a major role. So we consider averages of solutions over the boundary layer. And we will look more closely at the behavior of these averages. It is not surprising, more or less the standard theory of traces teaches us that under the assumptions we have, these averages converge as epsilon goes to 0 to the trace of the limit. On the way, we notice that the trace of the limit equals the limit of the traces. And here, the traces are computed at the epsilon distance from the actual boundary. And let me stress that all these computations are nice and relatively easy because of our choice of the domain. It is the geometry is very simple. That's why everything goes nicely. And if we gather all this information, we can pass to the limit in the weak form of the equation. And we see that what we have here is nothing else but the weak form of the heat equation with the dynamic boundary condition. So far so good. It was easy. But now the question is, we computed the limit, and we are wondering if the limit is a gradient flow. And what is the functional whose gradient flow is it? So we identified that the limit is a gradient flow of the functional E naught, but this functional is defined on a bigger space than the space we were dealing with earlier, because it is earlier we dealt with L2, or maybe weighted L2, but now we have L2 without any weight, but it is we take its Cartesian product with L2 over the boundary. And we define the limiting functional E naught in the following way. This is the usual Dirichlet integral. However, we compute it when the second component of the datum equals the trace of U. Otherwise, this function is defined as plus infinity. And it is relatively easy to check that the gradient flow of this functional is indeed the heat equation with the dynamic boundary conditions. Okay, and let me say that at the moment I haven't stated that our functionals E converge in any sense to functional E naught. For the moment, I'm not talking about it. I will come to this issue later. After solving an easy problem, I would like to switch to a slightly more involved one. And since I promised to talk about strong solutions, I somehow promised to deal with traces, or even traces of normal derivatives. And let me recall that we have a weight in the equation. So this equation is not uniformly elliptic. We have degeneracy at the boundary. Okay. And first of all, I would like to check that if I introduce the following functional, E epsilon, if I compute the subdifferential, which is here, then we see that indeed equation 7 is a gradient flow of functional E epsilon. Okay? And if we look at this identity, we deduce that in fact, the A epsilon times the normal derivative of U at the boundary must vanish, but must vanish in a very weak sense as a functional over the space of traces of H1 functions. Okay? But nonetheless, we have some information about the trace, which is implicit. Okay, so we see that we do have some boundary conditions, and as a matter of fact, we can improve this information because. Okay, I was saying I was going too fast. First of all, I would like to say that we can solve the equation we stated in a sense of nonlinear semigroups. Okay, this is a linear semigroup anyway. So anyway, we claim existence and uniqueness. Okay, and let me come back to the traces. It turns out that the compound object, which is A epsilon times the normal derivative vanishes as a function at the boundary. And let me stress that we know very well what is the normal component. This is plus or minus the unit vector of the parallel to the x, the last axis. Okay, so the good news is that we know how to compute the trace of this quantity, and it is an honest L2 function. And let me also record further properties of the traces. We will use them in the future, and they are similar to that what I stated earlier. And now there is a twist. When I talked about weak solutions, I needed just bounds which were coming from the gradient flow to pass to the limit. When I deal with the strong solutions, I need some more information because I want to control the traces of the normal derivatives. For this purpose, we had to establish what we call Rayleigh type identity. Rayleigh proved an identity which is similar to what we state here, but in a quite general setting of differential geometry. Here, the differential geometry is very, very simple. And the content related to the differential equations is much better visible. So let me stress that let me recall that our domain is torus cross an interval. So suppose we have U, which is in L2, the energy is finite, and diverges A epsilon grad U is in L2. Then this divergence squared equals this expression. And the value of this expression is that each mixed derivative, each second order derivative is square integral. Of course, we have to include the weight. Moreover, and this is the value added here, we have some control over the normal traces. And this is very important for us. And if you wonder how to prove this, basically you prove this as a well-known identity for the Laplacian. If you consider that Laplacian squared, if you consider Laplacian in a rectangle with zero boundary conditions and some information on the second derivatives, then you can derive this identity. So the proof is basically the same. You integrate by parts and you have to be careful. So I skip completely the proof of this. And now let me come to the questions I would like to address. The question which has been studied for some time is, suppose we have a sequence of functionals which converge, which gamma converge to something. In this case, we call it E epsilon. Does this convergence imply convergence of the gradient flows to a solution to the gradient flow? We know that in general the answer is negative, unless we have some additional information. And this additional information is the Geology energy dissipation balance. And I will derive such a balance for our problem. And let me compute, since here we have to compute gamma limits of functionals E epsilon. Let me start with these computations. So, and we notice one interesting thing. If we compute the gamma limit of E epsilon, then we obtain E bar. But let me stress that this computation is using the L2 topology, not weighted L2 topology, just L2 topology. And we see that something is not correct, because we are aiming at obtaining the heat equation with the dynamic boundary conditions, and we know that this is a gradient flow of a different functional. So we see that something went wrong. So possibly we are using a wrong topology when we are computing the gamma limits, because the L2 topology does not take into account any concentration phenomena. So we have to try to compute examples to check what happens. Okay, and so eventually we will pass to the limit, and we will face the question. Suppose we have a family of solutions to the gradient flows of functions E epsilon, and now epsilon is non-negative, so I include E naught. And we are asking the question about what is the correct notion of the convergence such that E epsilon indeed converges to E naught. And first of all, I will deal with the question when we have the weight function B epsilon such that the height of the weight is equal the reciprocal of the width. So as I said, I would like to first compute gamma limits and to see what goes wrong. Okay. So one of the functionals we have to deal with is this one, and we will see that such a functional appears when we compute the a priori estimates. So, but I would like first to talk about gamma convergence. And let's try to compute, let's try to compute the gamma limit. We see here that the weight will force some creation of the boundary phenomena. And we have already seen such a thing. Okay? So at this moment, we are deciding to switch to a different notion of gamma convergence. So we introduce the following notion. Suppose we have normed spaces x epsilon and x naught, and we have a mapping iota which goes from x epsilon to x naught. And we say that a family E epsilon gamma converges to E naught with respect to iota if we have the usual lower semi-continuity part, but usually we say that V epsilon goes to V, but now we are writing iota epsilon on V epsilon goes to V in X naught, and we have the usual recovery sequence. And let's see what happens here. Here we pick up X epsilon, which is L2 over the space cylinder, with the norm, which is a weighted norm. Okay, we have integration in time and space, but we are using the same weight function. And the limiting space x0 is the usual L2 over the space-time interval cross L2 over the boundary. Let me recall that x sigma t is the boundary of omega times the time interval with the natural product. Okay? And so you see this is a bigger space than the space we did initially. And we have to introduce the mapping iota. And we introduce it in a simple way. Okay, so we have to define the first and the second coordinate. So the first coordinate is just an embedding, and the second coordinate is the average. Okay, I wrote two formulas to be correct because our boundary has two components. So we have to average over two boundary layers. Okay? And we are saying that if we have f epsilon, function f epsilon defined on the previous slide, then it gamma converges to fbs with respect to iota, where the limit functional has the following form. As a matter of fact, checking this is not difficult, but you need a good definition of the convergence. And there is one additional piece of information we have to gather is, as a matter of fact, we will see that we have in our energy balance such a term. And we don't know, I don't know how to compute the gamma limit or gamma limit with respect to iota, but what is sufficient for us is the following lower semi-continuity result. In other words, here we pick up the Laplacian and the boundary term. And here, what is important, we can prove this result only because we have the Rayleigh identity. And it's clear that the mixed boundary terms, I mean, the second derivatives disappear because the boundary layer shrinks. But here we see that we pick up explicitly the normal component, the normal the derivative at the boundary. Okay. So what happens? After computing the gamma limits, let me derive the energy dissipation balance. So first of all, I recall the equation. So what we do first is we multiply this equation by the solution and integrate by parts. So we pick the first identity, which is very nice, but it's not crucial. The second identity is more important because we multiply equation 10 by the time derivative. And here, this is important that we are dealing with strong solutions because here the time derivative is well defined as a function. So we may compute its square and integrate. So we pick up this identity. And this is not sufficient. And this identity is nice, but it does not involve all the ingredients of the equation. It is not the necessary energy dissipation balance. In order to get the energy dissipation balance, we are proceeding in the following way. We are squaring this equation. So maybe I will switch the color. We are squaring, sorry, I'm squaring this equation. Okay. And after squaring, I divide by the weight, b epsilon. And then, look, here we have 1 in front of this term. And here I have 1/2. So the other 1/2, to the other 1/2, I apply what I just computed. So this is the other piece of the energy dissipation inequality, which is important. So here I use the very deep inequality that 1 is 1/2 plus 1/2. Okay, and let me stress one more thing, that this equation I wrote here is valid for all alphas, the exponent alphas in the weight, and I will use it later to play with the weight, to play with alphas. And now we are ready to pass to the limit. Okay, so okay. So here's our theorem. We study first case alpha equal to 1. So we suppose that we have a well-prepared data. Right? Then our solution to the gradient flow with beta, it would be, converges in the following sense. And let me stress that the averages of the boundary layers have the following nice properties. The time derivatives converge to minus the trace of the normal derivative of the limit. However, this convergence is very poor. So we have the correct convergence to the correct object, but in a very poor sense. Nonetheless, we are satisfied. Moreover, the limit is correct one. I mean, the limit is a solution to the heat equation with the dynamic boundary conditions. And how do we do this? We start with the energy dissipation balance. Okay, and we wish to pass to the limit. I guess I have 2 minutes, so I will skip the details. So the point is, we are able to pass to the limit of epsilon in this energy dissipation balance to get so let me come back. I'm able to pass to the limit in the energy dissipation balance. And then I have another energy dissipation balance, and I take the time derivative of this guy. And this is the result of the differentiation. And when I have this identity, which is valid for almost every t, I can deduce that this energy dissipation balance comes from, gives me the heat equation with the dynamic boundary conditions, and this is written here.
So, in order to leave time for 1 or 2 questions, you should finish very soon.
And exactly, this is the end of my story, because from this equation is nothing else but the heat equation with the dynamic boundary conditions. Okay, let me stress here that this is sum raised to the power 2. So thank you for your attention.
Yeah, thank you very much for the talk. So the talk is open for questions now. You can just raise your hand. I don't see any questions. Oh, Jose Francisco had a question. Yeah?
Yes, I have a question. I raised the hand. May I?
Sure.
Well, interesting result that reminds me something that I did with Pierluigi Colli about 30 years ago. Can you just please remind me what is exactly your theorem? Because as far as I can understand, this is a boundary layer when you get in the limit, the time derivative in the boundary. Is that right?
Okay, sorry, let me come back to the theorem. So this is the theorem. So we start, let me write the equation. So the equation is B epsilon ut epsilon.
Yes, the initial condition is in which space? It's a strong, we have a strong solution, is that right?
Yes, that's right, that's right.
Okay. Because, well, as far as I understand, this is a little, well, if you have a strong solution without a non-homogeneous term, this is natural. But as far as I understand, if this is the same problem, but you may check yourself, I can just share with you in the chat some reference.
I would appreciate.
Yes, so you can just share with this reference. And in fact, it seems that we can do it in more general for weaker solutions. And we have also considered the Signorini problem. And it depends also on the rate of the singular term and the epsilon. Because the epsilon is this layer, isn't it? It's a boundary layer, if I understand well.
Yes.
Okay. Then this epsilon should be balanced with the singular term that you call singular, which is a kind of diffusion coefficient somewhere, or a fusion, or I mean, we call it. I think was this ratio was sigma, and there is this alpha, which is the product of both. And I think this is a phenomena which is larger, because it also happens for second order differential equations, for wave equations, for instance. You can have the second derivative on time also on the boundary, provided you have linear operators. So maybe it's not the same problem, because I was just finding this very similar to what I did with Pierluigi Colli more than 30 years ago. But you have now the reference, and you can go to see if there is.
Thank you very much for your comment. But let me stress one more thing. Okay, I'm going to the wrong direction. We were dealing with, our point is to exploit the Rayleigh type identity, which permit us to talk about the traces of the normal derivative. So,
yes.
Okay. So we have a breakout session for extra questions to the speaker. I think this is a perfect theme to be discussed in more detail, maybe in this breakout session after the next talk, because otherwise we are getting a bit tight.